Good morning, everyone. Welcome to the second Elixir Friday Coffee. And we are going to present all the tools and services this infrastructure is providing to the users. This time, this is David Jakubec, who will be presenting the two tools, which is the INTAA and 3DPatch for exploration of energetics and conservation of biomolecular structure. David is currently affiliated both with the Faculty of Mathematics and Physics, Charles University, and also at the IOCB. The webinar will be about 20-25 minutes. If you will have any question, please use the chat on the right corner of that screen, and David will try to answer that question. So David, please, the floor is yours.
Thank you for the introduction, Jiří. I will start by saying that I did not develop these tools just by myself, and in particular the first one was developed in collaboration with my colleagues at IOCB, and the other one was developed in collaboration with Rob Finn from Amble EBI in Kingston as part of an Elixir Staff Exchange program. So let's get to it. The first tool I'm going to talk about is the Inta, the Interactions of Amino Acids web server. This is a web server which is focused on the interactive interaction with and visualization of energetics and conservation in biomolecular 3D structures. The web server consists of two components. One of them is the amino acid nucleotide interactions web server, which focuses on a static analysis of interactions between amino acids and nucleotides in 3D structures of protein nucleic acid complexes. In this talk, I'm going to focus on the other component called the Interaction Energy Matrix, IEM, web application. This web application is primarily used to calculate the interaction energies of various components, such as residues or whole chains, in biomolecular 3D structures. The idea behind this is that the net or total interaction energy of a particular residue is related to its role in the stabilization of the 3D structure. In addition, this web application integrates a pipeline for calculation of evolutionary conservation of the amino acid residues and thus allows the user to link these two views on the protein structure. So let's get to it. In this tutorial, I will be using this structure as an example. It's a structure of a homeodomain, which is a small soluble DNA binding protein. So I will be using this identifier and its corresponding sequence. This is the front end of the Inta web application server. As I said, there are the two components, amino acid nucleotide interaction web server and the IEM web application. So let's get to it. Once I start the application, I am asked to enter an identifier of a protein structure. So we can do that. Or I can upload a structure myself. Then I am given the option to choose the parameters of the interaction energy calculation pipeline. The interaction energy calculation pipeline utilizes a molecular mechanical force field, which we can choose. We can use any of the or one of the commonly used force fields, such as OPLS, charm, or amber force field. We will use the charm force field in this case. We are given the option to add hydrogen atoms to the structure, the hydrogen atoms need to be present there for the calculation to work. In this case, we don't have to add any, because we are working with an NMR structure in which hydrogens are present. But if we are working with an X-ray structure, we can add them using a reduce program. Finally, we have the option to choose a model or a dielectric model to use in our calculations, whether we want to simulate a water-like environment or perform the calculation in the gas phase. we will use the water-like environment and submit our job. In the interface, we can see a taskbar where all our jobs are visible, all the jobs present in the session, and we can easily switch between them if we want to. The calculation is already finished. The interface of the IEM web application primarily involves a list of residues. I will refer to this as the first list, a list of residues present in the 3D structure. This list is seen twice, and we will get to both of them in time. The residues are initially sorted according to the identifier of the residue, but what we are primarily interested in is the total interaction energy of the residues. If we want to look at the residues sorted according to their role in the stabilization of the protein, we can simply sort the list by the net interaction energy of the residue. The net interaction energy of a residue is the sum of its pairwise interactions with all other residues in the structure. On the right-hand side, we can see a visualization of the structure in an integrated 3D molecular viewer. Once we select a residue, that residue is shown in a stick representation in the 3D structure. Now I've chosen a glutamic acid residue, which is the residue with the most favorable interaction energy in the whole structure. In the second list of residues, I can now see the pairwise interaction energies of the selected residue with all other residues in the structure. If I want to identify which pairwise interaction is the most favorable, I can sort this list according to energy. Again, I can select the second residue, in this case this arginine, and it becomes represented in a stick representation in the molecular viewer. In this way, I have identified one of the, if not the, most favorable interaction in the 3D structure. We can visually confirm this. In this case, we can see a salt bridge between these two residues, and we would naturally expect this to be favorable. The 3D structure is initially colored according to the total interaction energy of the residues. If we want to, we can switch this to a pairwise interaction energy visualization, in which case the structure is colored according to the interaction energies of the first residue with all other residues in the structure, where red colors correspond to favorable interactions and blue correspond to unfavorable interactions. We can easily switch the visualization to conservation mode to see how the evolutionary conservation relates to the 3D structure. In this case, we can see that these two amino acid residues are not particularly highly conserved. We can see the information content of the residues in the bar below, and we can see that it's somewhere in the middle. If we want to find the most conserved residues, we can easily sort the first list according to the information content. And for example, identify, now I have selected the most conserved residue, which is the tryptophan, and thus identify, for example, the hydrophobic core of the protein. In this case, the core consists of the tryptophan, this phenylalanine, and this other phenylalanine, and we can see that they are all very highly conserved. The user can switch, instead of the 3D structure, the user can visualize the interaction energy matrix as a two-dimensional array. Can make it larger, where we can see all the interactions in one view. If the user wishes to do so, the array can be exported. Finally, Right now, we were looking at the interactions of the whole amino acid residues, but if we wish to do so, we can also look specifically at the interactions between the backbone atoms, the side chains atoms, and so on. If we have a multi-chain structure, we can also look at the total interaction energies between the various chains present in the structure. That's it for the INTAA web application. It's publicly available. You can go there right now, and there is an associated publication if you wish to read out more about it. Also, the application features an extensive help page where all the details and windows are explained in greater detail. The other application I talked today is 3DPatch, which is a client-side web application which utilizes federated application programming interfaces, APIs, of other services to perform homology searches and identification of similar 3D structures for protein sequence or profile hidden Markov model queries. As I said, this application is the result of an ELIXIR staff exchange program of 2017. Its source code is publicly available. The website is accessible as well, and there is an associated publication. So let's get to it. I will copy the sequence of our example structure now. This is the 3DPatch web application. So I can start a new search by entering a sequence. I could also submit a profile hidden Markov model if I wish to do so. We will submit. What happens when I enter a sequence on 3DPatch? The sequence query is sent to the API of the Hammer web server, and a search against the UniProt reference proteomes database is performed. This yields me a multiple sequence alignment. This multiple sequence alignment is converted into a profile hidden Markov model. This profile hidden Markov model is then used to find similar structures in the protein databank in Europe, again using a Hammer search, yielding me a list of structures, of 3D structures, with sequence similar to my original query. At the same time, the information content profile is calculated for the profile hidden Markov model using the Skyline web server. And these results, the information content profile and the list of 3D structures, are then integrated in a 3DPatch to provide the user with a visualization of the 3D structures conservation. We can now see that our search is finished. I will get to this window. Here I can see a pictorial representation of the coverage of the intermediate profile hidden Markov model by the available structures. I can choose, for example, this structure for visualization, and it appears in the integrated structure viewer with an information content-based markup. If I wish to do so, I can choose any of the other similar structures from this list. In this case, I will choose the one home structure, which corresponds to our original query. And again, in the structure viewer window, I see the 3D structure visualized with the conservation-based markup. In the other windows, I can see a representation of the information content profile of the profile hidden Markov model. And I can see the alignment of our input sequence used in the input window to the consensus sequence extracted from the profile HMM, and I can see the alignment of our selected structure to both of these sequences. I can interact with the aligned sequence to see the selected residues highlighted in the 3D structure viewer. Again, there is an extensive help page, which users can read and understand more about the details of the web server. You may see that I'm accessing this web server through a file protocol, and the reason for that is that currently there is an expired certificate, but so if you would like to try the web server now, you will unfortunately have to wait for a few days before it is available again. Oops, sorry. That's about it from me, and I thank you for tuning in, and I'm happy to answer any of your questions now.
Okay, David, thank you very much for a clear presentation, and hopefully the 3DPatch will be available quite fast. I don't see, yeah, I see one question. There is Wojciech who is asking, in some new cool bioinformatics application, for example, AlphaFold, there is a use of the concept of coevolution. Do you plan to go this way?
I don't think there are plans or currently plans to add this feature to the two services presented. It can be done in the future. It depends, really. I don't think it's planned currently because there are quite a few other options to do that yet available, but it can be added. It can be added if we want to in the future. But it would require to add other pipelines and visualization options than there are currently available, because what's available right now is focused on individual residues. So it could be added, and it could be added here and have, for example, coevolution available as an option similar to the pairwise interaction energy. That's true. That would be probably the best approach, but I don't think that's that's currently discussed.
Yeah, Marianne has another question. Is it possible to download INTAA and run it for all structures or a subset of PDB?
I can't answer this. I don't think so, but I'm not the one who put this server up, and I don't federate the actual web server. So you will probably have to ask Jakub Dalgonek, who is listening, to answer that. Although it would be useful. And similarly, there was a discussion yesterday about having an API, or that a similar service could have an API, which would be useful as well. But that's up to other people.
Jakub is here. Just the comment, we already did it for a few users who asked for the subset to be processed by INTAA. Currently, we do not have the workflow, for the, let's say, downloading INTAA and run it locally. But in the future, we can actually discuss that option too. Currently, we are actually serving users as a standalone application on our side. Okay, there's a Thomas, which is the last question. Maybe I missed that, but how are interaction energies computed? Are they force field based?
Yes, there is a molecular mechanical force field, which the user can select. And then there is a specialized implicit solvent model, which is not available in tools like GROMACS, I think, which is custom implemented, but those are molecular mechanical interaction energies.
Okay, I see last question, or this is the answer of Jakub. You can use the HTTP protocol to send a structure from the command line. So Marianne, I hope it satisfied your question. And because I don't see any other questions, so let me thank Jakub for David for presentation, and let's meet next Friday at the same time for another Elixir Friday Coffee presentation. Thank you very much for your attention, and see you next week. Bye-bye.
Thank you.